Alright, so now we're going to try and find the formula for this conoidal wave. So if we look at the system of equations we've got, we're actually just going to do the integration basically. It's quite good fun. So it's f squared into c minus 2f. That's the system of equations that we've got to try and solve. Okay, we're just assuming here for the moment that those constants of integration are equal to 0. Okay, so that is the case of this special travelling wave. We're only trying to find a solution. We're trying to find this very special solution, in fact. Okay, so we can rearrange that equation and we can get that the integral of the f, we just take the positive solution for the moment of the square root. And that is physically the only solution that can exist, and now we've got to do some integration on that base there. So this integration, you could type this into Maple or Wolfram Alpha, and they probably know how to do it. So the substitution is that we substitute f is equal to a half c sec squared of s. Alright, so what does that mean? It means that c minus 2f is going to be equal to something special, isn't it? So c minus 2f is going to be equal to c into 1 minus sec squared of s. And then there's this identity that 1 minus sec squared is equal to tan hyperbolic tangent squared. Okay. All right. Okay, so now we've got to work out, so that's going to make that nice and simple. Now we've got to work out what df ds is equal to. So this, change colour here, this is equal to, it's a half c into, so sec squared is 1 over sec squared is 1 over cosh squared, so it's 1 over, what is it? Cosh of s squared, so if I, to the minus 2. So if I differentiate that, df ds, I'm going to get minus 2 coming down from here, so I'm going to get minus c, and I'm going to get the derivative of cosh as sine over cosh of s cubed, okay, to the minus 3. Alright, so now I substitute all of this mess into the equation. What do I get? Kind of a miracle is going to happen here. We wouldn't have come up with this without a good scheme. So this integral here is going to become the integral of, now we've got ds times df ds, so minus c sine of s divided by cosh cubed s, and then we've also got the square root of that, which is going to be equal to, we've got multiplied by f, so that's a half c sec squared of s, which is cosh to the minus 2 of s, and then hyperbolic tangent, the square root of that, square root of c minus 2f, which is the square root of c times tan hyperbolic tangent, which of course is sine squared of s cosh to the minus 2 of s. ds is equal to the integral of d zeta. And have a look at this. Sine here, we get cosh to the minus 3, minus 2, minus 1, they all disappear. We get sine squared here I'm just trying to find my error. This shouldn't be, this thing here is the tan squared, but it's not tan squared, it's the square root of that, right? So that should be to the power of minus 1, just 1 there. Let's fix that up. All right. So the miracle does happen. And this is equal to, so all of the hyperbolic parts disappear. We've got a c, we've got a half, we've got a square root of c. The c cancels. So we've got 1 over 2 square root c. Okay, so I'm going to clear this page off. I'm just going to rub out the top here so we can carry on and solve all of this. Okay, whoops, I've made a mistake here as well. Just looking at my solution. This should be a minus 2 on top. Okay, it's divided by half. All right. So our equation was the integral of minus 2 over the square root of c ds equals the integral of d zeta. So that gives us minus 2 the square root of c times s is equal to zeta plus a constant. And then we've got to rearrange and work out what s is equal to. So we'll just write it down here. So s is equal to the square root of c over 2 with a minus zeta plus a, and s, finally we go back to our original substitution, which is f is a half c sec squared of s. So the function f must be a half c sec squared of, and then we can get rid of the minus here because sec's an even function in any case, so we'll just get rid of the minus just from the fact that sec is even. So there is the function. We're almost at the solution here. Okay. So finally, we've got, going back to my original colour, I'm changing colour here, sorry. We've got zeta is x minus ct, so the travelling wave f, and of course the time coordinate is arbitrary, so this constant here is not really very important. We get f is a half c sec hyperbolic secant squared of the square root of c over 2 x minus ct plus a. So there's the formula for the solitary wave. If I draw a picture of it, it looks like that. And the height here, the speed, and the width and the speed are related. You can see here if c increases, it gets taller, but it gets narrower. So the faster moving ones, interesting properties of this picture of these just quickly, right? This is a half c. Oops. The height is c over 2, but the width here is like approximately 1 over square root of c, if you want to think about it. So the next, a faster travelling one will be taller and steeper, okay, which is something that actually John Scott Russell, he worked that relationship out. But there's the formula there and there's the integration. It's not too scary an integration, that.